want you guys to look at the top equations first, okay? So we're not going to actually do example 1, and we're actually going to skip example 2 too, just because we had our homework quiz today, so we have to balance our time a little bit. But if you were going to solve the problems in example 1, what would you do? Jenna? Okay, so one option is to move the constants to the same side as all the other terms, and then you could use quadratic formula, or you could factor it once you have it set equal to 0. How else could you solve these? Then? Okay, so setting it to 0 factoring, setting it to 0 in quadratic formula, and there's one other way that we could still solve these. Anela? Yeah, so these ones you could actually square root also. Do you guys see why we have that option here, but we don't always have that option? Like at first glance at example 3, we feel like we might not have that option because there's like x squareds and then there's x's. So we feel like we can't just like square root something and get rid of it. However, in those first ones, everything is inside of the squared. So square rooting is another option that we could use. Now, on the homework quiz that you guys just took, okay, you guys had to find intercepts of that equation written in vertex form, right? And what did you do in the process of doing that? Did you guys square root? Okay, that's what we did when we took notes on it, okay, that we got the squared part alone and then we square rooted. So whenever all the x's are in the squared part, we can square root. So it seems like example 3, you can't do that. Example 1, parts A and B, you could do that, okay? But there's actually a way for us to rewrite example 3 where we could do that because it's really special. So right now, if we look at example 3, how it says x squared plus 12x plus 36, that factors as a perfect square. So because that can be written as a perfect square, like this is the same thing as x plus 6 squared, there is an option to solve this one by square rooting as well. Okay? It didn't seem like it at first, but if it's a perfect square, then we could. Am I saying you have to do it that way? No, but our focus on this lesson is going to be to learn how to do it this way so that we can use that as a tool if we choose. Okay? So once everything is part of a perfect square and you get the squared part alone and everything on the other side, we can square root and we get x plus 6 is equal to plus or minus 3. And then this gives us our 2 solution options when we go to get x alone. So x is going to equal negative 6, because we're going to move that 6 to the other side, plus or minus 3, and we can finish those 2 options. Negative 6 plus 3 would be negative 3, and negative 6 minus 3 would be negative 9. So those would be the 2 solutions. So what we're going to talk about today is completing the square. Why you would want to complete the square, we kind of have 2 motivations. Motivation number 1, so that we could possibly use square rooting as a method of solving, and we don't have to use the quadratic formula or factoring, okay? Option 2, what if I don't want an equation written in standard form, and I would prefer it to be written in vertex form? Then I need that perfect square, so I have to make a perfect square whether it exists there or not. The nice thing about example 3, and this was put here really strategically on purpose, is that this stuff over here was already a nice perfect square, right? So completing the square is the idea that we use to deal with the fact when somebody doesn't give us the nice perfect square, how can we make it a nice perfect square? That's essentially all we're doing with completing the square, okay? Either to rewrite stuff or to solve stuff in this manner. Okay? So here are 3 expressions that don't have a constant in them, and our job is to figure out which constant would make them a perfect square. Okay? So remember, that means 2 of the exact same factors. So some of you probably remember the formula, but if you don't, let's establish like the idea of where it comes from, because that deep understanding is better for us. So if this says x squared plus 18x plus something, if we were looking for a perfect square, 2 of the exact same factors to make that, they'd have to both start with x so that we get the x squared. Okay? We don't know what the end number is, and we have the freedom to make it whatever we want, but we know the middle number is 18. So what would you have to have 2 of here, 1 in each factor, in order to make that middle number of 18? Alex? 9. Okay, we'd have to have 9 is the only way that we can get those, right? Now 9 doesn't answer the actual question. The actual question is, what constant do I put in that C spot? But now that you know that 9 is the only way to make these the exact same thing to get 18 in the middle, what number does that dictate has to be in that C spot when you multiply this out? 81, right? The 9 times 9 will make 81. Okay? So this one was kind of nice because 18 is a number that we could nicely split in half, right? They get less nice as we move across here because of the 9, here because of the 2 in the front, okay? So if we want to be really proficient at this, and they're not all going to be really nice and easy for us to figure out like this, we want to find the pattern of what we did, okay? So first, how did we establish the 9 number? What part of the quadratic did we look at, and what did we do to it? So how did we get 9? I see Jenna and Zen and Anila, and they all already answered questions for us. Claire. Good. We took half of B, specifically that middle term, right? So in order to establish 9, we took the B value and we cut it in half from our equation. Okay? But that didn't finish the problem. It just kind of gave us the idea of what number would be in the factors. But then what did we have to do with that 9 to figure out the number that we would actually use as the constant would be 81? What's the relationship between the 9 that we got and the 81 that we had to put in the problem? Alex? We squared it, right? So we're establishing the fact like, wow, you can take that middle term and cut it in half to know what should have been here, and then that times itself is always going to make the last number, so squaring it will always make the last number. So this is kind of the general process of completing the square. How do we know what number should be at the end to make it a perfect square? We do this, okay? However, this was really specific to having our stuff just start with x squared, kind of like how we've been studying our transformations, and we really have to have that x minus h group. It can't say like 2x minus h or anything like that. That changes the whole process. The same is true. So I can't just do C like I did part A. I can't just take 18 divided by 2 and square it. It's different because the 2 is in front of the r. So we'll talk about how to deal with that in a minute. But this is the general idea. If you can get x squared by itself at the beginning, no coefficient, then you can just take the b value, divide it by 2, and square it, and you'll know which number should be at the end so that it factors of 2 of the exact same factors, a perfect square. Okay? So, looking at part B, the number's not as nice, right? The number's 9, and we're just going to deal with fractions. You'll see when you actually solve these that the fractions are a little annoying. You have to add them or multiply them. However, they actually work out pretty well when you have to take square roots and stuff like this to finish solving. So we're just going to leave it in fraction form. So according to our pattern, B fits the pattern. R squared has no coefficient in front of it, but the B value is not an even number. So we would take negative 9. We would divide it by 2. I'm just going to leave it as that fraction since it doesn't simplify it. And we would square it, and that would give us 81 over 4. And that's probably not something that you were looking forward to seeing, but we just have to accept the fact that in this case, because that middle term has an odd coefficient in front of it, it's going to be a little more complicated to split it equally into these two parts. Okay? Is this all right with everybody so far? Sen? Mm-hmm. It would be both minuses in here. So if both of these became minus, the end term is still positive, but the middle term will be a negative value instead of a plus. Is that okay? Yeah. And then we'll see that when we go through and factor them afterwards. So to deal with part C, we know it can't be the same as part A because it has a 2 as the lead coefficient. But our pattern only works when a 1 is the lead coefficient. So we kind of want to think of this like we do when we are doing our transformations. If we've only studied this with a 1 as a lead coefficient, we basically need to remove the 2. But it's not an equation where there's like 2 sides and you can just cancel it out. So when we remove the 2, the best we can do is kind of factor the 2 out. which kind of leaves us with this idea. Okay, the 18 is now a 9, and we're still looking for something at the end. So now, this problem right here is actually a complete repeat of part B, right? It's r squared minus 9r. What would you add on to the end? So we've already done that arithmetic. We would take 9 divided by 2 and square it, and that would give us 81 over 4. So 81 over 4 is the number that would make that a perfect square. However, it is not what C is. Can anybody tell me what C is going to be? Graham? Double that. Do you guys know why he's saying double that? 81 over 4 completed the square for this polynomial, but that was after the 2 was removed. Now to know what number would really sit there, I have to put 2 back into all, make it look just like that. So this would be 2r squared minus 18r plus 2 times. So I get 81 over 2 would be in that spot. Okay. So 1, we established this kind of little formula we can use for completing the square. And 2, we should have established that we can only do it when the lead coefficient is 1. And when the lead coefficient is not 1, we kind of manipulate it for a second. And then we have to put it back in to see what we're really dealing with. Is this okay with everybody? Okay. How many of you guys remember completing the square really well? How many of you guys have feelings of hatred towards completing the square? Yeah, okay, it's okay. Thanks for your honesty. Period 5 was very vocal about how they feel about completing the square. They're not excited about it at all. So I'm sure today's going to be great in period 5. All right, so I honestly, like, at the end of the unit, you can choose how to solve however you want. That's the goal. And so we can solve by factoring. We can solve by using the quadratic formula. We can also solve by completing the square. So by the time we get to the end of the unit, I will no longer dictate how you solve something. I will not include in the directions solve by completing the square. However, in this specific portion, I want you to experience completing the square so you can make an informed decision as to if it's something you want to do later. Plus, we need it for 2 other things. We need it to write it in Vertex form, and we need it later on to write equations of circles and some other things that you'll explore in like pre-calc. Okay? So we're going to solve part A by completing the square, even though completing the square probably wouldn't be the method I would choose for that. It's totally factorable, and I would just factor that real quick and solve. But our goal here is to get practice with completing the square. Okay? So if we were going to complete the square, we need a perfect square, and right now that's not a perfect square. So how we deal with that in an equation is we basically take the 120 and put it on the other side of the equation, and we're going to decide our own constant that we want to put in here. So that might seem unfair, like we're changing the problem, but with an equation, remember, you have the ability to do whatever you want to one side of the equation as long as you also do it to the other side. So I can make whatever I want here as long as that number also shows up in equal balance on the other side. Okay? What number would complete the square on the left side of the equation? Like in order for this to be a perfect square, we want this to be x squared plus 2x plus, how do we figure it out if we don't know? Anybody new? How do we figure it out? What was the little formula we just came up with to complete the square? Kyla. Good, the 2. So we take the 2, we divide it by 2, that would be 1, and we square that, which would still be 1. So 1 is the amount I want to add to this side. And then in order to not have changed the equation, I need to add that same amount to the other side. If you did it correctly, this should factor as a perfect square. Okay, if you go through the factoring process. If it doesn't, then you probably you're either factoring wrong or you chose the wrong thing to add to complete the square. Okay, and this side happens to be 121. Okay. And then this is where we could use square roots to solve again like we've been using before. So we'd square root. We'd get x plus 1 is equal to plus or minus 11. So x is equal to negative 1 plus or minus 11. And we can do both of those little sums and differences to figure out the value of x. So negative 1 plus 11 is 10, and negative 1 minus 11 is negative 12. All right, somebody give us a starting point for part B. Jenna? Good. The 2 is an issue, right? We know we can't go through the completing the square process if we want that there. I'm actually going to move the 12 over and then take out the 2, if that's okay with you guys. It doesn't matter the order that you do that in. And this case, we actually have a little more freedom. We don't just have to write the 2 out. We can actually, this time, cancel the 2 out. Because I can divide by 2 because now there's 2 sides to the equation. So I can divide by 2 on this side as long as I divide by 2 on this side. Okay? And so after dividing everything by 2, here's what this equation looks like. And I'm leaving a little space because I know my goal right now. I know I'm trying to complete the square, so I know I'm trying to add in a different constant there. Okay? Looks a little bit ugly, right? All right, so to complete the square, we have to take what's already here, divide it by 2. This doesn't count. We have to divide it by 2 ourselves, and then square it, okay? 7 over 2 divided by 2 is the same thing as 7 over 2 times a half, okay? So the dividing by 2 part gives me 7 over 4, and then I need to take that and square it. So the beautiful number that I'm going to add here is going to be 49 over 16. Okay? And I'm going to add that same amount to the other side. Now again, you might not like that number, but if it's correct, it should work out pretty well. So 49 over 16 is the square of 7 over 4. That means that this polynomial should factor with x and 7 over 4. And then here's what Zen was asking about earlier. If this is a negative in here instead of a positive, all that changes is that this has to be an x minus 7 over 4 here. That way it makes a negative middle term because 2 negatives add together and are still negative. But the end term is still positive because negative times negative gives us that positive. Okay. On this side, I do want to make a common denominator so I can just add them all together. So I'm going to multiply top and bottom by 16. And 6 times 16, let's see, would be 96. Okay. So on this side, I'm going to have 6 denominator, which you might be hating, but remember, you're eventually taking a square root. So I'm actually very excited that the denominator is 16 instead of something like 3 or 5 or something that's not a perfect square. This is going to work out well when I have a square root. Okay. And then negative 96 plus 49 is going to be 47, negative 47. Okay. And then we would go to square root. And then what issue are we going to have here? The square root of a negative, which we're going to learn a little later in this unit we can deal with. Okay. There are some numbers that no one has told you about yet. The real numbers are not all the numbers in the number systems that people created. So we'll deal with that. But for right now, we would stop and say there's no real solution to this. Okay? There's no real number that I can get for x as a solution. I'm going to try and squeeze in one writing vertex form, and then that's it. Okay? So the other way we'd want to use this, so solving, not so great. This is why people have hatred towards completing the square, right? It's like a lot of steps. You'd rather like just bust out the quadratic formula or something like this. However, it's great for rewriting, and you will need it for rewriting for some other things. So we're actually going to just look at B, the harder example, and we want to change it to vertex form. Okay? So we want a perfect square piece, and then we can have a constant out here. So do you guys see how I just separated my constant? Because 10 is not the perfect square. Okay, so I'm taking it out. Now, the 2 can't be in here if I'm going to make a perfect square. So the next thing I'm going to do is factor the 2 out like we did in that first example. And I'm going to leave space for me to add in what I want. Okay? We just did the work for 7 over 2, so let's not repeat it. What number has to come complete the square if this is 7 over 2? We divided it by 2 and squared it in the last problem. So 49 over 16. Now, you can put the same amount on the other side, or if this is a positive amount, we can subtract it side and have balanced our equation also. Do you guys get that? Like I could add 5 and subtract 5 and I've really done nothing, but I wrote extra numbers down. It says 49 over 16, but how much did I really put in here? The 49 over 16 is being multiplied by 2, which really the 2 would cancel with the 16, makes it 49 over 8. So I'm going to write a number here that does not look the same, because it's not about what you wrote, it's about how much that is worth, okay? This said 49 over 16, but because it was being multiplied by something, it's actually a different amount. Is that okay with everybody why this number doesn't exactly match? Okay? If this wasn't here, I wouldn't have that issue. Okay? And so now I can write this in vertex form. I have a 2. I can factor my perfect square. And then I would want to make common denominators here. So that would be like 31 over 8. And now my equation's in vertex form instead of standard form. Okay. Again, there are some other ways to do it with quadratics, but we need completing the square when we get to circles and stuff like this. So it doesn't have to be your favorite, but I need you to know how to do it. Okay. So this assignment, the skill 7 homework, part of it is on completing the square and part of it's on quadratic formula. So you guys can completely start it. Tomorrow we're going to cover the quadratic formula portion of it and review what we call the discriminant and make sure you guys know that. But again, it has 2 parts like the graphing did, how I had vertex form and standard form. So it's a bigger homework assignment. So my advice would be don't not do skill 7 right now just because it says it's not due till Monday unless you want a lot of homework over the weekend. I would do part of it right now. That's from lesson 4-6 on completing the square tonight. And then tomorrow night, I would do the part on quadratic formula. Or if you're like a quadratic formula expert and you want to get more done tonight to not have as much over the weekend, then you could even start that second part. Okay?